So, welcome to the all new episode, the story of the stars, the celebrity of night sky. So, like we are traveling a lot, we are the past few days we are doing a lot of sessions based on astronomy as we are celebrating the Astronomy Heritage Week. So, we are ending this session. We are ending this Astronomy Heritage Week by our last and important session, the story of the stars, the celebrity of the night sky. So, like as we all know, like looking at the night sky is always a treat to the eyes. But beyond these twinkling dots, there are all sorts of stars that are beautiful and fascinating. They also hold key to the mysteries of the universe. For centuries, humans have tried unravel and spectacular lives of stars. We have learned quite a lot in the process, but there is still so much that remains unknown. As we all know, yes, humans have long gazed towards the heavens, searching to put meaning and order to universe around them. Although the movement of constellations, the pattern imprinted on the night sky were the easiest to track, other celestial events such as eclipses and the motion of the planets were also charted and predicted. Historically, astronomy has focused on observations of heavenly bodies. It is close cousin to astrophysics. Succinctly, the put astrophysics involves the study of the physics of astronomy and concentrates on the behavior of properties and motion of objects out there. However, modern astronomy includes many elements of the motions and characteristics of the bodies, and the two terms are interchangeable today. So, like in the broader perspective, like we are like in the present time, we study like the astronomy in the two broader parts. One is observational astronomy, and other one is theoretical astronomy. I'm not going like very deep into this, but by telling you the main important types of fields of astronomy, like the one is. In observational astronomy, we directly focus on the direct study of stars, planets, and galaxies. While in the theoretical astronomy, we discuss about the model and analyze how systems have evolved. So I am not taking too much time of you as our esteemed host is also waiting to take the session. So let me introduce to her. So SKYAAC VIPNET Club, Ignited Minds VIPNET Club, WLS VIPNET Club, EduStem Initiative Global, in collaboration with the Sky Foundation, in its series of Astronomy Delights, presents before all the episode 9 in the form of a short talk on the story of stars, the celebrity of the night sky, by Ms. Poojan Agarwal, astrophysicist and OzGraw PhD scholar, Center for Astrophysics, Physics and Supercomputing, Swinburne University of Technology, Australia. In this talk, the speaker discussed some ways in which we can study stars, telling the story through a Hertzsprung-Russell diagram and the importance of the lives of these stars in the present day astrophysical problems. So let me tell you something more about Ms. Poojan Agarwal. Like joining the National Center for Radio Astrophysics in the Winter School Student Program in 2012. After that, she went for UT Radio Telescope Program, and later on she also went for IUCA as a project student in 2015 and 16. After that, she went for Melbourne in the Swinburne University of Technology as a researcher, as PhD at Center of Astrophysics and Supercomputing. So welcome. I also want to tell you something more about Ms. Poojan Agarwal. Like since my early days, I used to know Poojan Di. I used to call her Poojan Di, as we all are a part of UPAC members. So it's very nice to see someone from our group went to Australia and researching in astrophysics. So welcome to Poojan Di, and thanks a lot for like today's session. Thank you. Welcome to Poojan Di.
Thank you so much, Swapnil, for this really beautiful introduction. And first of all, am I audible? Everyone, you can hear me clearly?
Poojan Di,
Yes,
you
ma'am.
are good.
Yes, ma'am.
Yes,
You are
ma'am.
heard clearly. Yes, ma'am. Yes, ma'am.
Thank you. Okay, once again, hello everyone. And once again, thank you, Swapnil, so much for this really beautiful introduction. I'm really delighted to be here and once again amongst my old folks to present something about what I do here. And after this beautiful introduction, let's look at something more beautiful, the topic of today's talk, night sky. Night sky, whenever we look at it, is beautiful, dotted with tiny white dots. For centuries, this night sky has fascinated humankind, be it photographers, artists, poets, or astronomers, or maybe even a combination of these. But behind these twinkling white dots, there are beautiful objects. There are stars, there are planets, galaxies, and even star clusters. For today's talk, we'll be focusing only on two of them, on stars and star clusters. When I say the word stars, the very first thing, the very first image that comes in our mind is that of our own sun, our nearest and dearest star. Unfortunately, our star or sun is not that exciting. Why? Because there are many more stars out there of different mass and size. Stars that are much bigger and brighter than our sun, and stars which are much smaller. And today, we'll be looking into the lives of each of these stars. But before that, I will introduce you to a tool, an astronomer's tool or an HR diagram. And finally, we will see why stellar evolution is so important. All right, back to the picture of night sky. All of you, I imagine you're all amateur astronomers, so you have seen night sky, you have wondered at different constellations, and one such constellation, Centauri, if you look at it, at one part you will be able to find a fudgy patch of light, Omega Centauri. This is through a small telescope. But what happens if we use even much bigger space telescopes like Hubble? Let's have a closer look. We can see that fuzzy patch of light, Omega Centauri, starts resolving itself into countless number of stars. These stars, as we zoom in even more and more, you can see that there are some features emerging or some patterns emerging in them. There are stars of different colors and different brightness. Now, we can do two things. First, we can sort these stars on the basis of their color. Next, we can sort these again on the basis of their brightness. And when we do that, the result is an HR diagram. It's an important tool to study stellar evolution. But let's look at the individual component and how do we get here. Let's start with the brightness. Again, talking about night sky, when we look closely, we can see that there are different stars, and these stars are of different brightness. Some stars are brighter than the others, while others are dimmer. Now, this different brightness of stars gives us an important clue about stars themselves. It tells us about the size of a star. But wait, there's a catch. Imagine a street light on a road. All these street lights, they are of same size, they are of same brightness, but ones which are closer to you appear much brighter than the one farther away. It's because, similarly, stars which are closer to us, they appear brighter than the one far, far away. So we also need to take into account the distance of these stars in order to study them. And so we have this term apparent versus absolute brightness. So apparent brightness is the brightness of star as it is. And for the absolute brightness, we place all the stars at a standard distance of 10 parsec. Before I go further, let's comprehend the term 1 parsec. Now, we know the distance between Earth and Sun is 1 astronomical unit, while the distance between Earth and our second nearest star, Proxima Centauri, is roughly 1 parsec. So 10 parsec distance will be 10 times of distance between Earth and our second nearest star. Now, just consider an example. Our sun, the brightest object in the sky, which is so bright, is a source of all light and energy during the day. When this star is placed at a distance of 10 parsec, it's much smaller. It's even smaller than what I have shown here. I couldn't make it smaller, otherwise it won't be visible on the screen. Not even our sun, even other stars. For example, Sirius in the constellation Canis Major is the brightest star in the night sky. But if we place all the stars in this constellation at same distance of 10 parsec, we see that Sirius is not so bright anymore. Now, all this exercise of brightness of stars and distance and everything, it tells us an important quantity about stars themselves, which is luminosity or total energy output of a star. Well, this is one thing. Now, let's talk about the second bit. Let's talk about colors. And to understand this, we need to again come closer back to our home and start with an iron nail. Generally, an iron nail is a cold black object, right? Let's take a flame and start heating it. That cold dark object starts turning red. You heat it more, starts turning white. Heat it more, it becomes, from cold red iron rod, it becomes red, then yellow, white, and so on. So all this heat actually, and all these colors, they indicate the temperature of iron rod. And the very same thing happens in stars as well. In stars, the color of a star is indicative of its surface temperature. For example, a blue star is much hotter than a yellow star like our sun, which again is hotter than a red star. And we can do all this and again come back to a picture of HR diagram. And when we put all the nearest stars that we see in this HR diagram, we can see there are these different patterns emerging in this special diagram. Let's analyze these patterns one by one. Starting from this band which runs across this whole diagram, the band of main sequence stars. Well, these are stars like our sun. All these stars have one thing in common. They are burning hydrogen in the center. Now, exists a whole variety in these main sequence stars. There are very small M-type stars or red stars, and all the way up to there are big, bright, and blue O-type stars. Our sun is a G-type star here. And all these stars are the beginning of a stellar life. And depending on their masses, for example, these are low mass stars here, and these are more massive ones, they lead slightly different lives. Now, these stars, these red-yellow stars, when they evolve, they become red giant stars. This portion of HR diagram. Now, these red giant stars are 10 to 100 times larger than our sun. Example would be in the constellation Taurus, the brightest star, Aldebaran, is a red giant star. It is 40 times larger than our sun. In fact, our own sun will one day become a red giant star. And when it does, it will surpass Earth's orbit. But don't worry, it will still take billions of years to do so, and we are safe and sound until then. From red giant stars, there are even bigger stars, supergiant stars. These big blue stars, when they evolve, they become blue and red supergiants. In the constellation Orion, the second brightest star, Rigel, is in fact a blue supergiant star. Such stars can be 75 times larger than our sun. And in the same constellation, the brightest star, Betelgeuse, is a red supergiant star. It's even bigger. How much? It's 1,000 times larger than our sun. I have placed sun in the same picture, but it's difficult to see. You can see it's that tiny dot. To understand this number better, let's look at a video. Let's place Betelgeuse in our own solar system. So this is our solar system and sun in the center of it. Now let's place Betelgeuse in the same place. We see Betelgeuse is as big as the orbit of Jupiter. But if you think this is the biggest star, no, they are even bigger hypergiant stars. These stars are 1500 to 2000 times larger than our sun. They are really, really big. This was all on the big side. Now let's take a step back. Let's look at something tiny, the dwarf stars. There are different categories of dwarf stars as well. But one portion that I would like to start is this lower end of main sequence stars. These are red dwarf stars or M-type stars. A fascinating thing about these stars is these are the most common kind of stars in the universe. Our second nearest star, Proxima Centauri, is in fact a red dwarf star itself. When compared to Sun, Proxima Centauri is just 15% the size of Sun. And even more, there are white dwarf stars. Now, unlike red dwarfs, these stars are not burning hydrogen or even any element in their core. These are dead stars made up of electron degenerate matter. These stars are mostly found engulfed in beautiful planetary nebula. These are the end product of low mass stars and are roughly the size of our Earth. All right, doing all this exercise tells us something good about the core lives of stars. We see that all stars, they start their life in this portion in the form of a nebula. They form a protostars, and the less massive stars like our sun and other red orange stars, they burn hydrogen in their cores, evolve to become a red giant star, and finally, when they can burn elements up to carbon and oxygen in their core. And when they're not able to burn further elements, they slowly shed off their outer layers to form these planetary nebula and ending their life as a white dwarf. More massive stars, like Rigel or blue stars, they can burn elements all the way up to iron, becoming blue and red supergiant in the process, and finally ending their life as supernova, and to become either a black hole or a neutron star. But this was all on the observational side. Let's look at the second side. How do we model the lives of these stars? Well, to do so, scientists have a tool. We have some computer programs which can model the structure and evolution of the stars. All right, so this is the second aspect. So all this while I was talking about how do we observe stars. But we can also, with the help of computer programs, can simulate the lives of these stars. And this is with the help of stellar structures and evolution codes. Now, these computer programs, what they do, so all the stellar life, we can condense it in the form of some equations. Now, these heavy-looking equations, there are computers program which can solve these equations for different points inside the star to get a stellar model. Now, this stellar model, when evolved in time, gives a stellar track. Now, let's see how we can simulate this life of our sun. So, this is our sun. It starts its life, a star like our sun. It starts its life somewhere on this corner, and it slowly burns hydrogen in its core, increasing in brightness. And at the end, when it has finished hydrogen in the core is not hot enough to ignite helium. And therefore, it expands and becomes a red giant star. But as it does so, the core contracts and heats up. And finally, this star is able to ignite helium. It ignites helium, it burns helium in this blue loop, and finally burns carbon and oxygen. And that's it. It's not able to form elements beyond oxygen, and so it pulsates here on this giant branch and slowly sheds off its outer envelope to become a white dwarf. Now, a star which is 10 times or 15 times the mass of our sun lives its life slightly differently. This star, it is much bigger and brighter to start with, and this star, when it finishes burning hydrogen in the core, is still hot enough to burn other elements, so it evolves, becomes blue and red supergiant in the process, is able to burn all the elements all the way up to iron, and then explode and end its life as a supernova. Similar to these two stars, we can trace evolution of stars born with different initial masses on the HR diagram. These different paths that are traced by these stars, they're known as stellar tracks, and you can kind of compare them with these railway tracks. But these railway tracks in itself, they don't do anything. And hence we do not see these stellar tracks in nature. What we see in reality, for example, for this, even with railway tracks, we do see that trains at some point passing through it. And that's the same thing to observe when we look at stars in the night sky or in our neighborhood. We see stars evolving at some portion of this HR diagram, but again, tracing these different paths throughout this lifetime. All right. This is, before I go into this third and final segment, I would like to ask, are there any pressing questions? Is there anything, any question that one would like to ask, or any doubts until this part?
Don't worry, ma'am.
Don't worry, ma'am. We are just making a note of the questions, and we shall be taking in the end at the final composite interactive session.
Okay. So let's look at why studying the lives of these stars is so important. First of all, we should answer the question, do we really understand everything about stars? The answer is no, we don't. Most stars in our galaxy, they are formed in a binary system, similar to the Alpha Centauri system A and B in the constellation Centaurus. So these stars are two single stars evolving independently, but then they are close enough to each other that they can interact with each other. So if one of the stars, it evolves and becomes a giant star, the other star can suck in material from this one. And this alters the lives of not just one, but both these stars. Now, when these stars, if they are at the end of their lives, for example, if they are neutron stars and black holes, and if they are close enough, they can alter the gravitational field around them and can generate ripples in space-time. These ripples in space-time are called as gravitational waves, and these can be detected by detectors such as LIGO and Virgo in USA and Italy. Now, these gravitational waves, first detected 5 years ago, have opened up a new window to study universe. They have told us many new secrets about these stars and their lives. One thing that they have told us is this. In this diagram, we see neutron stars that we observe through other means, and black holes that we observe through electromagnetic radiation, usual light. But then there are these blue portions, these blue black holes, which merge and form even massive black holes, and that give rise to gravitational waves that we can detect. Now, all these gravitational wave detections have told us that there exist much more massive black holes than we originally knew. We do not know how these very massive black holes form and also how they merge. This is something scientists around the world are trying to understand. This is one problem or one thing of why we need to study lives of stars, because these black holes are neutron stars and are the end product of stellar life. There is one more thing. There are beautiful clusters of stars. Now, globular clusters, these are gravitationally bound systems of tens of thousands to millions of stars, are contained in a distance of some 10 to 100 parsec, and they are found in the center of our galaxy. Now, these globular clusters, they are very fascinating. So let's again look at how do we model these stars, or what's the recipe of making these globular clusters. It's very easy. You take in some single stars, you take some binary stars, mix them together, and throw in Newton's law of gravitation. And what you will get is something on the right side. You see that these bunch of stars are not only evolving, they're living their life, but they're also interacting with each other. And these are all single stars and binary stars. All this interaction can change how these stars evolve. It can also make two stars, which were essentially single, to form binary systems. And through different interactions, it can also lead to destructions of stars already in binary. These globular clusters are an important tool for studying stellar evolution. For decades, we thought that the stars in these globular clusters were formed at the same time and out of same materials. Hence, they will have same chemical composition. But in the past decade, we have realized that there is some problem with this picture. We have realized that globular clusters, they contain not just the primordial population, where each star has similar chemical composition, they also contain the second population of stars. In the second population, or the second type of stars that we have seen in globular clusters, they contain some extra elements. And these extra elements also show some relation between them. There are some elements which are directly, their abundance is correlated with each other, while other elements, they are anti-correlated with each other. This is one thing. There is one more problem. In 2007, in NGC 2808, we saw, scientists were trying to observe a constellation in this globular cluster in the constellation Carina, with the help of Hubble Space Telescope. We saw that the HR diagram of these globular cluster is slightly different. And this difference can be explained by a different amount of helium in these stars. So far, we have found that these different or multiple stellar populations are not only found in that cluster, but are in almost every globular clusters that we know. And all these are indicative of one thing. They're telling us that there is hydrogen burning happening at much higher temperatures, so much higher than what we usually know about stars, at roughly 75 million Kelvin. Now, these high temperatures are found inside very massive stars. For example, stars which are more than 10 times the mass of our sun. But the problem is these stars have these stars are rare and have short life. So we need to study their lives and how they interact with each other through computer simulation. And this is exactly what I am doing for my research work, while also taking into account contribution from other factors. Well, me and scientists around the world try to solve these problems. We can tell two things. First thing is, we still don't know answer to these questions, and the mystery of both these problems continues. But whatever theories we come up with, when we try to match them with observation, they both will tell us something about stars and their lives. And while we do that, you all sit back, relax, and keep looking at the stars, because you never know what surprise universe will throw at us. Thank you.
So thanks a lot, Poojan ma'am, for such a very, very nice, superb, scintillating, and stupendous talk from your part. So I am just, you can say, remembering a few famous lines from Jean Taylor. Twinkle, twinkle, little star, how I wonder what you are, up above the world so high and like a diamond in the sky. Let me summarize the entire talk of Poojan ma'am, and so that we can proceed on to the interactive session for the day, because I am seeing a whole bunch of questions in the chat box. So I can just remember that twinkle, twinkle, little star may allow, may lull a baby to sleep. But beyond the confines of the earth or the atmosphere, exactly these words aren't accurate. This is the gist of the talk of Poojan ma'am. A correct, albeit less soothing rendition of this rhyme in the astronomical terms may be emit, gigantic ball of gas. So with this, I take a special word of thanks for Poojan ma'am for addressing the audiences, and especially as a breather to our esteemed speaker, I would just like to give a small happening for the day. Today is a special day because today we are celebrating the second anniversary of the Women-led Science Club, which is a co-organizer for us. I take it as an opportunity to congratulate the founder members of the Women-led Science Club and the coordinator Shweta Srivastav ji, because a small journey that started on this very same day in 2018 has emerged the club to an international platform and has been recognized by the Vigyan Prasar, the statutory body of the government of India of late, with the articles featuring in Curiosity and the workshops going on at the local, the state and the national level. And today we are collaborating with each other with the shared resources for celebrating the different days, Earth Day, Innovation Day, Copyright Day, the Book Day, and we are celebrating, as we all know, the Astronomy Delight series. So without wasting any time, I would just move on to the interactive session for the day. And I would just like to open the session with a few questions, a very few tricky questions that I have received over the mail from Mr. S.S. Jaini again. And before I mute myself up, Poojan ma'am, I would just like to pose a couple of questions which are related. And also our audiences, as we are having a few time constraints. So what we shall be doing is, we will be combining a few questions of the like-minded nature, and we shall surely try to find out the answers of them with the consent of the speaker. So the first question of the day that I can see from Mr. A.K. Jaini is, that is, what does nuclear fission has to do with the birth of stars? And where in the galaxy is the stars born? Over to you, Poojan ma'am.
I was only able to hear first part, but let me start with that. So all these stars, you see that they are emitting light, they're emitting radiation. But where does this radiation come from? Simple example: if you have a candle, you need to light it, and when a candle is burning something, you can see that it's emitting light. In a similar manner, these stars, they are in the center, they are fusing different elements. So these main sequence stars, for example, are fusing hydrogen in their core. This fusion releases lots of energy, which we see as these different twinkling dots in the sky. There are stars at later stages of their life. They are burning elements like helium and other elements. And all these nuclear fusion processes, they're releasing these different radiations that we can see. Amritanshu ji, can you repeat the second part of this question?
Sure, ma'am. Actually, the second part was, where in the galaxy the most stars are born?
Galaxy. Well, this is a complicated question, and the answer is not so straightforward. There are people who are scientists around the world who are trying to understand how these different star formation takes place in galaxies. But for sure, there are clumps of gases which are known as nebulae, and stars are formed in these nebulae regions. Well, for galaxies like our Milky Way, we see that most stars are concentrated towards the center, and as you move outwards towards the spiral arms, there are fewer and fewer stars. But then there are different galaxies, and they come in few different shapes and sizes. And we do not know whether these stars were there from the beginning or that some redistribution happened. So yeah, I really can't, I don't think anybody knows answer to this question, but I think I've kind of satisfied what you wanted to know.
Okay, thank you, ma'am. So I am just posing the next question in front of you. And then at the same time, I would just like to invite my co-host for the interactive session, Abhimanyu ji, also, that after I finish asking this question to Poojan ma'am, you can kindly take a note of the chat questions also. And by the time I will be browsing in for you. So we shall be taking on an alternative course. until the time limit reaches. So the next question for you, ma'am, is again coming from Muhammad Ismail, who has again joined us like yesterday from Dubai. He has asked, where does the space begin, and when stars die, what do they create? Over to you, Poojan ma'am.
Where does the space begins? This is something. Um, there is no particular answer to this question. I mean, we from what we know, what we have observed, we know that our universe was once formed in a big bang, and there is no edge to our universe. This is like really interesting thing or a fascinating thing about universe. All there is no everywhere we see, like there are stars and there are objects everywhere. And when these stars they die, the second part of the question, they don't go anywhere. They just they are there. They remain there only. For example, if stars they die and become a white dwarf, they remain in their places. However, if stars like neutron stars and black holes, when they die, they can travel slightly from their original distance because of the shock wave because of this shock wave they get because of supernova explosion. So yeah, when these stars die, they are still there in the sky. Some of them as white dwarfs, some of them traveling slowly if they can, as neutron stars and black hole. But even when I say that these rebound is very, very small and this motion is very small.
Thanks, Poojan ma'am. So, over to you, Abhimanyu.
Okay, so now just bringing the questions from the chat box. There are several questions, and again I'm going to combine the same mindset questions. So the first question to you, Poojan ma'am, is from Aditi Shukla. Is there any particular cause behind the different colors of stars? And a similar question, one more question has been raised, that if the stars are of different colors, so why we can see the star in the same color? So just over to you, ma'am.
Okay, that's a really interesting question. Yes, there is a reason, and that's what I explained in the talk. The reason for different colors of these stars is their surface temperature. So stars which are around which are less massive than our sun, which are, for example, just 80% of the mass of our sun, they are kind of red because they burn their elements slowly, they release less energy, and their surface is cool, comparatively cooler. But stars like our sun, they are releasing more energy because they have more mass, and therefore their surface temperature is higher, is hotter, and so we can see that okay, these are yellow. And even more massive stars, they are burning elements more rapidly, they're releasing even more energy, and so they are blue. Abhimanyu, can you repeat the second question?
Hello. The second question was that if the stars have different colors, so why from Earth we can see the stars in a single color? Why only we can see the stars white?
Yes, this is because our eyes are really good. Like we see everything with our eyes, but they are really insensitive. We can see a very small part of the spectrum of light. There are so many different wavelengths and colors, but we can see a very tiny fraction. And even so, we cannot differentiate between them a lot. So that's why when we look at stars in the night sky, we see that, okay, most of them are white. Sometimes we can see that, oh, some of them have slightly orangish tinge, or sometimes some of them are like slightly blue, but that's very tiny. We need the help of these telescopes, which are sensitive to these different colors, and only then we can study the different colors of stars.
So thank you for this satisfactory answer, ma'am. Now coming to the next question, which is from Kshitij Srivastava. What is the condition for two stars to become a binary star? Over to you, ma'am.
Before I answer this question, I'm really fascinated by all the beautiful questions, and these are like really good questions. All right, binary stars. Well, there is no particular condition for stars to become binary. Two stars, if they are close together, that they can be influenced by each other's gravity, then they are called a binary system. Now, if they're influenced by each other's gravity, sometimes these binary stars are born as a binary system. So, similar to how planets go around our sun, these binary stars go around each other. And when one of them becomes big enough, they can interact with the other star and can influence each other's life. Some other binary stars, like in the globular clusters, there are two stars which are essentially single. They were not in binary when they were formed, but because of interaction between these stars, they can actually come closer together and become a binary system.
So thanks a lot, Poojan ma'am. So actually, I have been bombarded with a whole lot of questions regarding the black hole. So I would just combine a few one by one, and then I would take the audiences on your behalf to the world of black holes also. So maybe possible a few people have been excited by the sci-fi, science fiction. So they are asking a few questions. So one is, now this is a scientific and interesting question. Could the Big Bang have started with a black hole exploding?
Okay, one thing, I am not an expert on black holes, but I will try to answer this question. So, okay, is it possible that our universe started with a black hole? Again, not just me, we really don't know if this is true, but from whatever we know, from the theories of Big Bang and how our universe came to be, in the beginning, there was nothing, not even a black hole. So this is difficult to understand. Like our brains, the world we live in is something very difficult to imagine that this can happen. But our universe started from nothing. There was no black hole or nothing. It just started out of nowhere. We don't know if this is true, but this is what theories say. And answer to this question, I don't think anybody can answer this.
Sure. Thanks a lot for such a candid reply, ma'am. So moving on to the next question, actually an interesting question again. It is because, can the Earth be ever sucked into a black hole? If so, what would happen? And then as a complimentary addendum, he has asked, what is the difference between a stellar and a planetary nebula? Over to you, ma'am.
Okay, can Earth be ever sucked into a black hole? Why not? A black hole has immense gravity, and because of its gravity, it can attract objects which are close to it. But the thing is, there is no black hole. There are black holes, but they are so far away that our Earth cannot feel the force of gravity of these black holes. So even for black holes, although they have very strong gravity, this gravitational force is limited to some region. It does not extend till infinity. So anything which comes closer than a particular distance from this black hole, only that object can feel that force of gravity of black hole. Only that object can be sucked by that black hole. So our Earth, technically, yes, it can be sucked by a black hole, but there is no black hole nearby. So we are very safe. There is even no neutron star nearby. And when I say nearby, I'm talking in terms of astronomical distances. So we can say that we are in really safe zone. Again, can you remind me of the second question?
Yeah, sure, ma'am. And so before I inform you of the next question, after this, the questions will be taken by Abhimanyu from the chat again. So this is the final question from the email. That is, what is the difference between a stellar and a planetary nebula?
Okay, well, they are essentially same. The two terms, they arise because of how and where do we find them. So planetary nebula, these are formed at the end of low mass stars' life. So when stars like our sun and even cooler stars, when they die, they end their life in the form of these white dwarfs and leave behind them planetary nebula. But if sufficient number of stars they do this, and also because of supernova and other factors, all this different gas and dust which is left behind, it can condense together and form new stars. And then it will be again a new phase, new stars forming out of this leftover gas, and those will be the star forming nurseries or stellar nebulae.
Thank you, ma'am. Now again, coming to the questions from the chat box. The questions goes to you is how does the sun produces energy? Over to you, ma'am.
Our sun produces energy by combining, doing the nuclear fusion of hydrogen and converting it into helium. So in the center of our star, our sun, we have this nuclear fusion reaction going on, and all this hydrogen, all these different hydrogen atoms are getting nucleus are getting converted into helium. And this process of making new elements actually creates lots of energy, at least until the formation of iron. And all that energy is coming out, and this is the one which powers our sun and also other stars.
Again, thank you, ma'am, for answering the question. Now, Shaurya Pratap Singh is asking that what gases are needed to create a new star?
Well, this is a question you can answer by yourself. As I said, that we need all these fusion reactions to happen, and this fusion starts with the lightest element, hydrogen. So one thing we need for sure is hydrogen to form these stars. But then the thing is, when I say fusion reaction, I often talk about, people talk about in very simple terms. There are different ways in this fusion reactions can happen, and other elements, they can act as a catalyst. So, for example, both a star like our sun and a star which is 15 times the mass of our sun, in their core will be fusing hydrogen. But our sun fuses it slightly differently, and this process is less efficient. So, for forming a star like our sun, you only need, for example, hydrogen. But for even more massive stars, they take help of elements such as carbon, nitrogen, and oxygen. And their way of forming helium from hydrogen is different. It releases much more energy and is much more efficient. So for those stars, you need even other elements. But essentially, in single line, you need hydrogen to make stars.
Okay. Now, Ayaz Aziz is asking that are black holes formed by these dead stars only?
Yes. So black holes are formed by stars which are 25 to 30 times the mass of sun when they start their life. So when I talk about all these different masses, I'm talking about mass of the star when it started fusing hydrogen in the core. Remember, as the stars evolve, they also lose mass. So yeah, stars which are 25 to 30 times the mass of sun, they can form black holes.
So thanks a lot, ma'am. And hopefully, if you allow us, then can we take one last question from the audience? It is because we are getting too many raised hands. There are still about 35 to 40 questions there. And I know that it's quite late up from the place we are talking to us. So dear audiences, with due apologies, I say that we have noted down all the questions, and there will be a question from my part and one from Abhimanyu's part that will conclude today's talk, but it is not the end. These questions will be answered via the Facebook page of the Sky Foundation. You can just move on to the Sky Foundation's page, and in due course of time, the questions that you have put, with the help and under the guidance of Ms. Poojan Agarwal, they shall be put over the relevant forum. So there are again a couple of questions, but they are on the same pattern by Mr. Suvit Shekhar and David D'Souza. Actually, you have more than almost answered the question of David D'Souza regarding that is what is the course of life after the fuel ends for a star that exceeds the Chandrasekhar limit. This is the technical word he has mentioned. So, and Suvit Shekhar has actually asked, what factor decides that a supernova will turn into a black hole or a neutron star? This is the penultimate question, and the last one will be taken by Abhimanyu. Over to you, Poojan.
Okay, what decides whether a star would become a neutron star or a black hole? Again, this is really good question, And I would like to answer it in two ways. One way is it is essentially the initial mass of star. So what happened when all these massive stars, this 10 to 15 times or even more massive than our sun, when these stars they form iron core, they can no longer burn this iron core. So what happens that all other elements, because of gravity, this core, it starts collapsing because of gravity. And this gravitational collapse creates a shock, a rebound, which results in the supernova. Now, depending on how big or small the core is, the force of gravity will be different. So for less, for stars which are like 10, 15 times the mass of our sun, for this, the gravity will be enough to that it can be stopped by the degeneracy pressure of neutrons, and hence the final product will be a neutron star. But if a star is much more massive, 25 or 30 times the mass of our sun, even the force degeneracy pressure of neutrons will not be enough to hold the object together, and it will collapse into a black hole. Now, the second answer, this is kind of a scientist view. This is what I said earlier, is a very simple one. And the thing is, we are still trying to study that how a star can form a neutron star versus a black hole under a different condition. And mass of star is one factor. The chemical composition of star and where it is in what kind of system, all these things also govern how whether a star would become a neutron star or a black hole. But in very simple, the very simple idea is, yes, it's most importantly is the initial mass of star or the mass of that core in the end, which decides whether a star would become a neutron star or a black hole.
Thank you, ma'am. Now, coming to the last question of the session, as we have many more questions, but the all questions will be answered on the Facebook page of Sky Foundation. So sorry for that, not putting the questions here. So the last question goes from Uttam Kumar Singh. Why does the star suck themselves when they are close? Why didn't they collide? Over to you, ma'am.
Okay, so this is, I think, with regards to binary star, that why is one star able to suck material from other stars? Why don't they collide? Well, just consider this. Why don't the planets in our solar system collide? There, in any such system, be it one star and its planetary system, or binary stars, or even triple systems, there are two forces acting on these stars. So one is the force of gravity, which is keeping these stars together. The other is the centrifugal force. So this force is similar to how you spin clothes in a washing machine. So you see that if you spin clothes, all these clothes, they tend to align on the outer boundary of your spinner. So because of the centrifugal force which is acting on these clothes. In stars as well, as they're orbiting around each other, the gravity tries to bring them close, but the centrifugal force, it keeps them apart. And that's why these stars are a stable distance. They don't just collide and fall into each other. But what happens? But if one of the star, it becomes big enough, for example, it becomes a giant star, it can enter into a region where the star of the force of other star, the gravitational force of other star, is high enough to suck in material slowly from this first star. And that's why we see this accretion of matter happening from one star to other star, the sucking in of material, and not just a direct collision. However, in some cases, stars can also collide and merge. But these are, I think, if I start talking about these stars, it will be way too long. So yeah, it's basically I think I will end here.
So thanks a lot, Poojan ma'am. We are really obliged to you that you spared your valuable time for us on behalf of Sky Foundation, Women-led Science Club, and all the coordinating institutions, I extend a very warm thanks to you. And before I hand over the proceedings to my younger brother Abhimanyu for proceeding for a formal vote of thanks on behalf of Sky Foundation, I would just like to again cite the final stanza from that famous nursery rhyme of Twinkle Twinkle. It says, "This your bright and tiny spark lights the traveler in the dark. Thou I know not know what you are, twinkle twinkle little star." So the mystery continues to unravel the new and new layers as we go on doing the latest and the latest of the research. So all the very best to all the travelers of the dark, we the citizens of this Mother Earth. And there were a few technical hiccups when your talk was there. I apologize to you, ma'am, on behalf of all the platform coordinating institutions. And with these words, I would just like to hand over today's technical platform to my younger brother, Abhimanyu, who kindly grace the occasion and present before us a formal vote of thanks to end today's session with the announcement for tomorrow. And before Abhimanyu joins, again, there is a small announcement that I would like to make, that our Sky Foundation and all the VIPNET clubs, we actually are planning to hold a session by a computer technical expert. It is because today in this age of lockdown, we are being forced to curb our movements as far as the general movement and all the things are concerned. We are more and more relying on the online platform, be it the different applications that we are using. This even Google Hangouts Meet is an online platform. We are doing digital transactions. We are on other different, we are doing online studies and all. So what are the, you can say, the dangers in which right now we are living with the advent of Facebook and WhatsApp? It is because sometimes you find that you receive a link over your mobile. You just click over your link and entire account becomes to a null account, and entire your hard-earned cash vanishes within a jiffy. So I would just like to invite the suggestions from the esteemed audiences that what could be the best part of the time where you can be present with us in the maximum presence, so that our expert can guide you all with how to proceed out properly without any risk, how to minimize the risk of phishing and all the technicalities that we have to face with the advent of the online technology. So this was a small announcement that I had to make on behalf of Sky Foundation and VIPNET and EduStem. So over to you, Manu, and good night from my part.
Thank you, Amritanshu for carrying over it to me. Well, I just want to start that looking at sky is always a gift to eyes, which several times makes you fantasize for knowing the beautiful, fascinating, and sometimes alluring mysteries of the infinite universe. But beyond these twinkling dots, there are all sorts of stars that are beautiful and eye-catching. For centuries, humans have tried to solve the spectacular lives of stars. I think we have learned quite a lot in the process, but there is still so much that remains unrevealed. In this talk, the speaker, Ms. Poojan Agarwal ma'am, has discussed some ways in which one can study stars, telling the story through Hertzsprung-Russell diagram and the importance of lives of these stars in the present day of astrophysical problem. I hope this session must be a knowledgeable bite for all of you. So now coming to an end, I, Abhimanyu from Sky Foundation, and on the behalf of WLS, VIPNET, SKYAAC VIPNET, EduStem Initiative, and Ignited Mind VIPNET wants to thank Ms. Poojan Agarwal, our today's esteemed speaker, an astrophysicist and OzGraw's Ph.D. scholar at Center of Astrophysics and Supercomputing from Swinburne University of Technology, Australia. I would also like to thank our superb audience for patiently hearing us. With this, today's episode comes to an end, but the series Astronomy Delight will continue till this Wednesday. So stay tuned with us, and you will all be informed by all our social media platforms. So keep following all our social media platforms, whether it is Facebook, Instagram, or anything. Hopefully, see you all tomorrow at the same time. In this pandemic COVID situation, we all suggest you to stay home, stay safe, and stay happy. Good night from my side, and wish you a very happy night sky watching ahead. And once again, thank you, Poojan ma'am, for this session.
Thank you all for giving me this opportunity. It was really, really great.